Okay, it's looking like attendance is kind of leveling off now, so maybe it makes sense to go ahead and get started. So welcome everybody to this installation of the Cafe University educational webinars. I am Rachel Nethery. I'm a assistant professor in biostatistics at the Harvard School of Public Health. I am a Cafe internal team member as well. And so I should say to start out that any views I express here today are my own and aren't meant to represent either those of Cafe or of my institution of Harvard or of the NIH. So everything I say here is in my own personal capacity as a researcher and educator. And so today we're going to be talking about processing and visualizing spatial data using R. And as I mentioned, this will be sort of a mix of slides and also interactive stuff going on in R for this webinar. And so particularly if you want to be able to work along with me in the interactive part of the webinar, please use this link or the QR code here to access the materials in a Google Drive folder. The link and the QR code take you to the same place. And so that Google Drive folder should have 4 files within it. You should probably download all of those onto your machine if you want to follow along interactively. Yeah, so once you have those downloaded, I'll give you just another second or so to do that. Once you have all those files downloaded onto your local machine, then we can get started. Let us know if you're having any trouble accessing things. And I think Allison, maybe folks are asking again for the link to be dropped in the chat if you wouldn't mind pasting it in. I should also mention that the wonderful Allison James is also joining us today for this webinar. She's also a Cafe internal team member working on the data team and is very experienced with R and spatial data processing. So she'll be kind of manning the chat. Feel free to ask any questions, and I will try to take a few breaks here and there to answer any questions that Allison would like me to weigh in on that have come up in the chat. So let's go ahead and jump into kind of some background and motivation. Feel free to go ahead, while I'm getting started here and open up your R Studio and your R script from that Google Drive folder, which you'll need maybe in the next 20-30 minutes or so. But I'm going to start out by going through a few slides, giving some motivation and talking about general spatial data types. So I'll go ahead and get into that. So we're going to be motivated here by climate epidemiology studies. We are the Climate and Health Research Coordinating Center. And so, of course, in climate epidemiology studies that look at associations between climate, weather, and natural hazard exposures and health, it's common to use maps to communicate patterns of exposure across space. So, of course, in this context, our exposures are pretty much always sort of spatially referenced in some way. Climate exposures usually come to us with information about geographic location of those exposures. And for the purposes of this talk, we're going to also assume that we have some health outcome data that we want to look at the association. We want to look at the association between that health outcome and some climate exposure. And we're going to assume that we also have spatial information on in that health outcome data. So you can imagine that this might look like, rates of disease for a particular geographic area or community. So in addition to just using maps sort of to display patterns across space, spatial data processing is also used in climate epidemiology studies because we typically want to sort of formally spatially link our health outcome data with weather or climate exposure data so that we can sort of formally analyze associations between these climate exposures and health outcomes. So again, we're going to assume that both any health data that we're working with and any climate exposure data that we're working with have some sort of spatial property, and that we should in theory be able to link them spatially, although we'll talk more about the details of how to do that later on. So in this tutorial, I'm hoping that you'll learn first the primary types of spatial data that we encounter in climate epidemiology. It certainly won't be an exhaustive introduction to all types of spatial data that we encounter in this space, but I hope to sort of make you familiar with the primary ones that we work with almost on a day-to-day basis in this space. We're going to hopefully learn for all of those commonly encountered types of spatial data how to import and process them in R, how to create effective maps, either for exploratory data analysis or for publications or for dashboards or things like that in R. And then we're going to talk a little bit about that point that I mentioned on the last slide of how to actually link different types of spatial data to assess associations between health outcomes and climate exposures. And so the background that I'm going to be assuming that you have going into this tutorial is basic familiarity with R coding and RStudio. Sorry, I'm just going to move around these Zoom boxes so I can see my slides better. Oh, here we go. Okay. So I'm going to assume that you are familiar with the basics of R coding, basic syntax, basic object types in R, and again, basic base R functions. I'm also going to assume that you're familiar with plotting and creating figures in ggplot, although if you're not, it wouldn't totally derail the experience here because we won't be exclusively relying on ggplot for our mapping. So you need some basic R familiarity. However, throughout this tutorial, I'm going to be assuming you have no prior experience with working with spatial data at all. So if you do have any prior experience, even very basic experience working with spatial data, you may be quite bored during this tutorial. So I'm assuming absolutely no prior experience dealing with spatial data in any capacity. That said, if you do want to follow along interactively with the R portions, the R coding portions of this tutorial, you will need to be able to install some of this key spatial R packages that we'll be relying on. So I'm hoping that even if you don't have those installed already, hopefully you would be able to get them installed on the fly today if you are wanting to work along interactively. So again, this really will be aimed at folks with no spatial data background whatsoever. And again, first part of this, I'll be going through some slides, and then in the later parts, we'll turn more towards an interactive session in R where we'll work through some real data examples. But first, I want to do a really quick and dirty intro to like the basics of spatial data. These things are things that you could spend an entire class, an entire semester-long class talking about. But what I'm really going to try to convey to you here is like the key information that you really need to get up and going for importing and processing and creating maps in R. So again, each of these next few slides could be an entire hour-and-a-half long lecture in and of itself. But we're going to sort of focus on giving you the essentials that you need to really get up and running with mapping as quickly as possible. So we're first going to talk about the two sort of classes of spatial data, which are vector data and raster data. So first, let's talk about vector data, because I think it's probably sort of the most familiar to you, just from interacting with maps in everyday life. So vector data is used to store data on spatial points, on lines, and on polygons. And then for any of those data types, points, lines, or polygons, you might have some associated information about those things that could also be stored in vector data. So let's talk through a little bit more concretely what examples of each of these types of data might be, particularly in the climate and health research space. So point data, spatial point data, could be something like locations of facilities that emit greenhouse gases. So for instance, you might have locations of power plants in the US, for instance, and those would be spatial point data where you actually have the coordinates, maybe the lat long, for these facilities. And then you might also have some associated information about those facilities, like how much they emit or what types of pollution or greenhouse gases they emit. So that's an example of point data, point spatial data that we might work with in the climate and health space. Vector data also includes line data. So probably the most common type of line data that we would work with in climate and health would be like road networks. So roads are typically stored as lines in terms of spatial data. So we could have this network of lines representing sort of road locations across the US. And then we could have some information associated with those road networks uh, corresponding to sort of density of vehicle traffic on those roads. And finally, the type of data that we're going to be mostly focused on, the type of vector data that we're going to be mostly focused on here is going to be polygon data. So when we say polygons, typically we're referring to polygons that represent the boundaries of some geographic areas of interest. Often these are sort of administrative geographic areas like states or counties. And so you can imagine that we might have data from these polygons, from these geographic areas, on the, for instance, the health of the population that lives within those areas. And indeed, health data are commonly reported on, for particular geographic areas. In the US, that's often counties or states. And I think in other countries, there are similar types of geographic units on which, administrative geographic units on which health data are commonly reported. So, so polygons, because they're this sort of common way of reporting health data, rates of a particular health outcome in a particular county or community, they're going to be our primary type of vector data that we're going to focus on here today. And so I should say, just before moving into talking about raster data, the other common class of spatial data, that one sort of key distinguishing feature between vector and raster data is, at least for me, I think about vector data as being useful for representing discrete spatial items. So that doesn't necessarily mean that the variables that we measure on our vector data have to be discrete, but the spatial items represented by the data themselves should be discrete items, like for instance, a discrete set of points or a discrete set of geographic areas or a discrete set of roads. And this is going to be in contrast to raster data, which we'll talk about on the next slide, which represents something that happens, a process that happens more continuously over space. So vector data are useful for representing sort of discrete spatial units. And I did just want to mention that, if you're US based and you're doing research in the US, this County Health Rankings website from the Robert Wood Johnson Foundation has a ton of really good county level health metrics for the US, and is a common source of data used for research and for creation of dashboards and things like that. So that's what you're seeing here in this life expectancy map. So the other class of spatial data is known as raster data. So raster data are just regular grids that have a bunch of cells, and all the cells are of equal size. And these cells are sometimes referred to as pixels. And for each of these pixels, we have an associated measure of a particular feature of interest at that location, at the location of that pixel. So each pixel corresponds to a spatial location on which we've measured some feature of interest. And again, what really distinguishes raster data from vector data, at least in my mind, is whereas the vector data that we talked about on the previous slide are best for storing information about sort of these discrete spatial items. Raster data, on the other hand, are really useful for storing values of spatially continuous phenomenon. So things like climate exposures, weather exposures, things like that, that aren't thought to sort of affect only discrete points. They're actually thought to sort of be able to be measured continuously across space. And so, as you can imagine then, in the climate and health data setting, it's common that climate exposure measures, which we do think about as being sort of more continuous over space and not confined to particular sets of locations or regions, those climate exposure measures are often reported on rasters. So I said that raster data are regular grids that have that are composed of cells of equal size. These are sometimes again referred to as pixels. So that by that I mean that within a given raster data set, these cells or pixels should all have the same size. And the size of those pixels is typically determined by the person who or organization who creates the data. And across different data sets, however, across different raster data sets, these cells or pixels could have vastly different sizes. So it's not like you always have the same size of cell or pixel across all raster data sets. And so the size of the cells or pixels in your raster data will sort of determine the spatial resolution or the sort of graininess of the resulting data set when you map it. So these are sort of two examples of raster data sets. One that uses relatively large cells or pixel sizes. And so here you can see that this, when you map these raster data, you get a sort of map that clearly shows that your data are represented on these pixels or cells, as sort of illustrated by the graininess or low resolution of this top map. Whereas in the bottom map, we're mapping sort of the same phenomenon, but on a raster where we use smaller grid cells, smaller pixels. And so what you can see here is that when you have raster data that use smaller pixels, have higher resolution, it might not actually even be obvious to the naked eye that these are pixelated data, that these are data on small grids, because you almost can't actually see the grid cells once you get to a higher resolution, as shown in this sort of bottom plot here. So you may get raster data in practice where you read in the data and the data just look like a smooth surface. And that's often the case when you have these sort of high resolution rasters where actually it becomes hard to detect the individual pixels and it starts to just look like a smooth surface. So in practice, when you're working with raster data, you can see sort of data that have these large pixels where it's very obvious that this is just a bunch of grid cells with different values, or you might have something that looks very smooth because the grid cells are very small and hard to detect with the naked eye. So again, in the health data, in the climate and health data space, it's often the situation that we encounter that we have exposures, climate exposures that are reported on rasters. So we have effectively raster data from which our exposures of interest arise. And then we have health outcome data that are measured for administrative areas or polygons. And to be clear, when I say that health outcomes are measured for administrative areas, this this type of health data could look a number of different ways. So for instance, you could actually have a data set where you just have a rate of a health outcome reported for every state or county in the US. So it would just look like a data set where the rows are states or counties, and for each one you have a rate of a particular disease of, for residents living within that area. Another way that you might see health data come to you is actually at the individual level, where, for a bunch of individuals in your study, you have sort of a row in your data set for each individual, and then there sort of some measure of a health outcome for each of those individuals. But often in climate and health studies, we hope that those individual level data would also contain some information about the location of residence of those individuals. So you might have some identifier in those individual level data of the county or the state or the administrative area in which each of those people live. And then what that would allow us to do, even if we're working with individual level data, would be to sort of link individuals with the climate exposure variables spatially based on their location of residence. So the health data could be sort of aggregated to some kind of administrative area, or it could be individual level with information about each individual's location of residence. And either way, we can use spatial information to link exposure and health outcome data. So to do this, again, because our exposures are usually reported on rasters and our outcomes are usually reported for polygons or geographic areas, what we often want to do is to convert the rasterized exposure data to the polygon level to create some kind of polygon level measure of each exposure that we can then merge in with the health data and look more formally look at associations. And so that's one of the big things that we're going to be talking about later in this session. And so before jumping into kind of working with our real data examples, I do want to talk about kind of the big sticking point in intro to spatial data, I think. This is definitely the trickiest concept, I think, for people to wrap their heads around when they're getting started with spatial data and mapping, which is projections. So I'm going to try to distill information about projections, which again could be an entire lecture or series of lectures in itself. I'm going to try to distill it just to the sort of minimum amount of information you need to know to get started and responsibly carry out spatial data operations and mapping. So I'm going to try to simplify it as much as possible, even though this topic can become very complex. So what are projections? When we're mapping and doing operations on spatial objects, we're almost always working in a two-dimensional space. We're assuming that we're working in 2 dimensions. But the reality of space is that the Earth is 3-dimensional. So the reality is that distances between things and shapes and areas of things on the globe are all should all really be represented in 3 dimensions. But when we're actually doing mapping and spatial data processing in practice, we're usually assuming that we're only working in a 2-dimensional space. So that means that we need to convert positions and the distances between them and areas from this reality of a 3D space to a 2-dimensional space. And so projections are the way that we do this conversion from the reality of the globe as 3-dimensional to our sort of 2-dimensional maps that we're going to be working with in practice. And so you might say, okay, good, I bet there's some sort of standard function that I can just plug my data into and it will do it will just do the projection, convert to 2 dimensions, and then we can move on with our lives. And the challenge here is that there's no sort of like one right, uniformly right sort of way to do projections of your data from 3 dimensions into 2 dimensions. The complication is that there are a lot of what are considered valid ways to do projections, but none that's sort of uniformly right for every area of the globe. And unfortunately, every projection, any projection of 3 dimensions to 2 dimensions, will inevitably produce distortions of the Earth's surface in some fashion, because it's not actually possible to convert from 3 dimensions to 2 dimensions and simultaneously preserve all areas, shapes, and distance properties. So to think about why this is, just you can maybe imagine a simple setting where you have a soccer ball and you slice that soccer ball open, and then you try to sort of take that material from the soccer ball and like flatten it out into a flat surface. You can imagine that that's actually going to be quite hard to do when you start to try to flatten it, because you're converting it from 3 dimensions to 2 dimensions. Some parts of the soccer ball are going to get like wrinkled up, maybe while others lay flat. Some will get wrinkled and their sizes will get distorted. And so the same thing is inevitable when we try to convert these positions on the Earth's surface from 3 dimensions to 2 dimensions. And so one common way of sort of doing this type of transition conversion from 3 dimensions to 2 dimensions is to kind of, again, slice the Earth between Alaska and Russia, effectively across the Pacific Ocean, and create a map like this, where we just sort of you can almost think about it as we like slice the Earth open and like unroll it. And so this is a common way of sort of projecting onto a 2-dimensional surface. However, one thing that you can immediately notice with this type of projection is that, so let's just focus on Greenland here, which is shown here. Hopefully you can see my mouse. So you can see Greenland here in the 3D Earth, which looks kind of like long and narrow. And then over here in the 2-dimensional Earth, Greenland is here, and now it looks kind of like fat and wide. And so you can see that by doing this projection, we've kind of distorted the shape of Greenland. And an even more sort of acute thing happens, for instance, with Antarctica when we do this type of conversion, because of course, Antarctica is sort of like a roughly round continent that's getting sort of stretched out into this long mess at the bottom here. And so those are just examples. This is just one example way to do a projection. And one example of the types, a few examples of the types of distortions that can happen. But there are all different types of ways to do projections and all different types of sort of ways of distorting things in space. And so you can see that, like, while these issues of distortion often are really acute, particularly at the poles, when you do these conversions to 2 dimensions, you can see that even for the US, these are 4 different valid projections of the US that all could lead to quite different sort of conclusions about the shape of the US, distances between things in the US. And so this just all sort of goes to show that the projection that you pick for your mapping is going to matter. And so then you might ask, well, how would I don't even know what any of these projections are. I don't even know what their names are. How do I go about picking one to use for my map that I want to make? And so the key here, this is again distilling down a lot of information and potential advice you could get in this space. But my recommendation is to just pick a projection that is tailored to the region of the Earth that you're working with. So there are different projections that are sort of tailored to focus on preserving the properties of distance, shape, and direction and area for particular parts of the globe. So your sort of main priority should be to pick a projection that is tailored to the region of the Earth that you're going to be working with. And then it should be tailored to sort of minimize distortions of these properties for that area. And so you can imagine, again, going back to like our soccer ball flattening out reference, it could actually be possible when you're trying to flatten out that soccer ball, it could be possible that you just focus on one little area of the soccer ball and you're able to get it to be quite flat and get everything for that little small area of the soccer ball to be quite well preserved when you flatten it out. But when you do that, that's probably going to mean that things get even more distorted on the edges or in other places away from that location that you focused on flattening out. And so that's essentially what we're doing, what we should be thinking about, how we should be thinking about it when we're trying to pick a projection for our map is we want to focus on one that is, where we focused, where the focus has been on sort of making a projection that nicely, neatly flattens out our area of interest, although it may sort of dramatically distort areas outside. So your next question might be, how do I actually even find out how to identify projections and how to put my data into those projections? So projections are identified by what we call CRS codes, coordinate reference system codes. And so really, before you start your data analysis and mapping, you should determine an appropriate projection and find its associated CRS code. Again, one that's tailored for the area, the region that you're working in. And so how would you do this? So there are a number of ways, and actually there are a number of R packages, I believe, that can help you pick projections for the particular spatial area that you're working with. But I think the simplest way to do it is to just go to this website, epsg.io. And it has a search bar at the top. You can type in the area that you're working with. So in our real data example a little bit later on, we're going to be working with a real data set from California. And so I just searched California here. And usually it will pop up with sort of the first hit in this search being sort of like one of the best projections to use for your spatial data when you're working with data from California. And so here, this was sort of our first hit. And this is indeed a good projection to use when working with data from California in the US. And so what we would want to do here in order to be able to tell R to use this projection is we want to um, identify this EPSG code number. So for any given projection, you'll have this EPSG followed by some number. And we want to identify that. So here our EPSG number is 3310. And we want to identify that, and we'll be using it later to tell R that this is the projection that we want to use for our California data. So again, when you're working with spatial objects in R, you'll want to check their initial coordinate reference system, what their initial projection is when you receive them, because they'll usually have some coordinate reference system already applied when you receive them. And then you may need to transform to your selected projection, which I'll show you how to do here shortly. So now that we've talked about a little bit of dry basics of mapping and spatial data, let's start into something that's a little bit more hands-on. And first, we're going to start with focusing on polygon data. So importing, processing, and mapping polygon data, and then I'll show you some examples of raster data afterwards. So let's first start by defining a little bit of terminology. So we commonly refer to features that are measured on spatial areas, geographic areas, or polygons as aerial data. So you'll hear me using that term sort of synonymously with polygon data throughout this presentation. So you can just assume that those, for our purposes here, are interchangeable. I'll talk about aerial or polygon data. These are data that are measured, features that are measured for geographic areas. And so what do aerial or polygon data look like typically when they come to us? So sometimes these types of data come in what are called shape files. And these are actually formally spatial file formats that contain both the area boundary information for the areas that you're working with, as well as the whatever features or information that you're interested in measuring on those areas, sort of all compiled together into this big spatial file. And these quote unquote shape files usually have a .shp extension, so you can identify them that way. What's confusing is that other times you actually may receive aerial data that come in standard data file formats that you could open in, say, Excel, like a CSV file. And so when aerial data come to us as something like a standard tabular data set in a CSV file, the data would typically have a column in them that contains a unique area identifier that you can use to merge that tabular data into an existing shape file that has the geographic boundary information for each area. And so we're going to show an example of this with our sort of real data tutorial here shortly. So again, you might get aerial data in shape files with an SHP extension, which you can directly read into R using some of the packages that we're going to talk about here in a second. And those will automatically have information about both the boundaries for each area and the features that you want to measure on each area. Or you might get a CSV file that just has these area identifiers, and then you need to figure out how to merge it in with an existing shape file that tells you about the boundaries. And so we're going to show an example of that here shortly. So the main package that we're going to be using for working with aerial data is the SF-R package, or Simple Features R package. There are a number of other package options for working with vector data in R, but SF is definitely by far the most popular these days. And some of the reasons I think that it's become so popular is because it simplifies spatial data in a way that a lot of other packages don't, such that the spatial data have a very familiar form, like a standard data frame in R. And you can use standard operations on the spatial data that you would on basically any other data frame. So it makes it really easy to apply sort of the functions that we already are used to working with in base R and various other packages to a spatial data set. Um, again, this SF package plays nicely with a lot of other popular R packages. It works nicely with tidyverse functions, and also is really well integrated with ggplot, which will help us easily make maps. It also has really great demos and documentation. It's available on CRAN, and it can be installed using your usual install.packages syntax. And if you are new to spatial data and you have never installed SF before, if you've never installed this package, I would recommend opening RStudio now if you want to follow along interactively, and trying this install.packages SF. It might take a few minutes to install. So if you want to work interactively, you might try going ahead and running that now while I'm getting things started for our more interactive session. So for our real data example that we're going to be working with for aerial data, I went ahead and downloaded and lightly cleaned some data from the US National Cancer Institute's State Cancer Profiles database. And these data tell us about the incidence rates of melanoma skin cancer by county for the state of California. So I pulled these data, cleaned them again very lightly, and have created a CSV file, which I provided to you in the Google Drive folder called ca_county_melanoma.csv. So you should see that in the Google Drive folder. And these are the data that we're going to be working with for our little interactive tutorial here. So you'll want to identify the location of that data that you've hopefully downloaded. And so we're going to show how to import these data into R. Note that these data are coming to us in a standard tabular file format and as a CSV file. And so that means that we're going to need to figure out how to link them in with the county boundary files before we can do anything like mapping. So we'll show how to do that. And then we'll show some examples of how to make maps with various different R packages. So let's now, oops. Then I can't move forward. Okay, there we go. So now let's switch over to our R script. If you're going to follow along interactively, you can open your R script now. And let's show some examples of how to import and then process and map polygon or aerial data. So at the top of this script, you'll see information about the handful of packages, R packages that we're going to be working with in this tutorial. First, I did load in the tidyverse package here, just because some of these mapping functions that we're going to be working with can become really clunky if you aren't able to use sort of like the piping syntax of tidyverse. And so just to keep the code clean, in some places I'm going to be using that like piping style syntax from tidyverse, although most of the code that I've written here is just in base R. So we'll just be using that piping syntax in a few places. So SF, again, is the simple features package for working with vector data in R. We'll be using that primarily for this part. I'm also here going to be working with the Tigris package, which I am using for sort of easy access to US administrative geographic boundary shape files. So remember that data set, that melanoma data set that we're going to be working with was just a CSV file. we're going to need to merge it in with a county boundary shapefile. And so I could actually go to US government websites and dig up that shapefile for county boundaries. But instead, I think the simplest way to get access to those data is just to use this Tigris R package, where it allows for easy import of US boundary shapefiles within R itself. So if you're going to, again, follow along interactively, you'll need to install this Tigris package. I've been using the Tigris package to access geographic boundary shapefiles for many, many years. It's always been an extremely stable and reliable R package, unlike some others. And then yesterday, as I was going back through and I wrote the code for this tutorial last week, and then yesterday when I went in to just rerun everything, make sure everything was working, I realized that suddenly a bug had come up in the Tigris package. It was a sort of recognized bug that was recognized by the creators of this package. I've never seen this happen with the Tigris package before. But it does require, I went on the website for the package and found that this was an issue that literally had just come up over this past weekend, the first weekend in April 2025. And so they recognized the issue and had created a patch for the problem with the package. And so if you want to work with the Tigris package, if you want to follow along here, just to note that in addition to installing the package, you might also need to run these 3 lines that install a patch for the package to deal with some instability issue that I had never encountered before with Tigris, that of course came up like one day before this tutorial. So, but in general, Tigris is a very stable package and a reliable way to get these US geographic boundary shapefiles. And once I installed this patch, it worked perfectly fine and normally. So you can run those couple of lines to get the patch if you want to follow along here. Also, for those who are outside the US, there are other packages that give easy access to more global geographic boundary shapefiles, like boundaries of countries, continents, etc. The main one that I'm familiar with is the R Natural Earth package, which has tons of boundaries for various different sort of levels of administrative units for countries across the whole globe. So highly recommend the R Natural Earth package in place of the Tigris package if you're working in global applications. Other packages that we'll be needing are the Terra package later for working with rasters. So this will be another key one that you'll definitely need to install if you want to follow along interactively. We'll use ggplot for static mapping, leaflet for interactive mapping, and then we'll use this cowplot library briefly just to create side-by-side maps. So you can go ahead, if you haven't already set your working directory, you can go ahead and start by setting your working directory to the path of wherever you downloaded the files from that Google Drive folder that I linked. I already have my working directory set, so I won't change it here. But let's go ahead and load in that melanoma data file, which again is this CA County melanoma.csv file. We'll load it in and save it in an object in R that we'll call melanoma. Let's look at what the data look like. You could use the view function, but I just prefer to use the head function because I think it can be more informative. So here's what the data look like. There are 2 columns and a bunch of rows. The first column is our unique US county identifier. And the second column is our data of interest for each county, which is the county's melanoma rate per 100,000 population. And so let's first talk about this FIPS column. So again, this is a unique US county identifying code, um, where the first two digits identify the state. And so 06, which is the first two numbers for all of our entries here. 06 is the state code for California, because remember, these melanoma data are only for the state of California. And then the last three digits identify the county within California. So in this data set, each row corresponds to a California county with its unique state code given in this FIPS column, and then its melanoma rate given in this melanoma rate column. And so this FIPS code is going to be key to merging in this melanoma data with a shape file that can be used for sort of getting the county boundaries and doing the mapping. And so remember, we said we're going to use this Tigris package to download the US county boundary shape files that we're going to use for this purpose. In addition to county boundaries, Tigris can also be used to download boundary shape files for almost any US administrative areas, including states, census tracts, ZCTAs, things like that. But for to get the county shape files, all you need to do is run this counties function within the Tigris package, and we'll save that out the shape file that it outputs to this cbounds object. And just a note that it might take a couple of minutes, depending on how fast your internet connection is and how much traffic there is. It might take a couple of minutes to actually get this county shape file imported. So we'll see that once this downloads, you can see the progress bar moving down here at the bottom of the console. Once this shape file actually downloads, by default, the output, the shape file, will be what we call an SF object. So that's an object, a shapefile object that's in the format used by this SF package for vector data that we're going to be relying on. So we're already going to have the data output from Tigris. We're going to have this shapefile that is already sort of in the format that we'd want it to be to use with this SF package that's commonly used for vector data processing. So these SF objects, remember, are handy. Objects from this SF package are handy because they look and act like standard data frames in R, of course, with a few nuances. But generally, once we get this shapefile object, we'll be able to kind of work with it and apply standard operations that we would in base R to any data frame. We'll be able to apply them sort of similarly to this county shapefile. And hopefully it's almost done downloading. I think my internet connection is a little slow, so yours might already be done. I see in the chat, some folks are getting an error. Remember up here that I said that you may need to uncomment these 3 lines and download this patch, because there's what I think is a temporary glitch with the package that is fixed by this patch. Again, I've never seen that happen before in all the years that I've been working with the Tigris package until I went to run this code yesterday in preparation. Oh yeah, and thanks, Allison. Once you download the patch, you probably have to restart your R session and rerun. And again, sorry for that inconvenience. Did not anticipate in advance that there would be an issue with that package, because it's always been extremely reliable for me. Okay, so now our for me, at least, my county shape file has been downloaded. And so now let's take a look at what the data look like just by using this head function. So basically, what we see here is that there's a bunch of stuff here printed at the top. Let's come back to that in a second. But then what's down here just looks like a standard kind of data frame, right? So we have all this mess that gets printed to us at the top. This is going to be telling us about the spatial information for the shapefile. And then everything else looks pretty much like a standard data set with a bunch of different columns in it. And then the last thing that I want you to note is that these simple features files should typically have as their last column a column called geometry. And that geometry column is going to contain the spatial information corresponding to your geographic areas. In this case, it's our county boundaries. So in this data set, each one of the rows represents a US county. And by default, this shapefile tells us quite a bit of basic information about the county. It tells us the name of the county, the land area, the water area of the county, so on and so forth. It has some basic county information. And then for each county, it has this geometry entry, which is going to tell us, or which is going to be sort of like used internally by the R mapping functions and spatial functions to tell those functions what the boundaries of this particular county are. And just a note that it's generally best not to mess with this geometry column, not to try to remove it or anything like that, or manipulate it in any way. So it's best to just sort of like leave that geometry column alone. Can cause problems if you try to mess around with it. So again, this looks like a sort of regular data frame, except for that geometry column and this spatial information at the top that's telling us a little bit about the spatial extent and the type of spatial data, the polygon data that we're working with. So first thing, just to demonstrate that we can sort of apply standard base R functions to these SF objects. Let's subset this US county shapefile data to only contain counties in California, since that's where our melanoma data are from. So to do this, we can apply the subset function as usual. This is a standard base R function. We can apply the subset function to our shapefile, telling it that we only want states where the state code is 06, which we said is the state code for California, and we'll save this subsetted data as a new object. And so now if we look at the top of this new object, you can see that all of these counties in the subsetted object are counties from California. So again, this just shows that you can use sort of your standard R functions on these simple features SF spatial data objects. And remember, we talked a lot about projections when we were in the slides, and we determined a projection that would be appropriate for using with our California data example. Specifically, it was this code here. It identifies the projection that we wanted. And so before changing a projection, let's just use this function stcrs to figure out what the current projection of this shapefile that we've imported is. So you see, this gives you a bunch of kind of ugly looking information when you run this stcrs function. But this like second line here is what tells you what the projection is. And so this is a code here that indicates that right now these data are actually unprojected in the sense that they're just represented as sort of lat long in standard lat long information without any formal projection applied. And so that's typically not what we want for mapping, again, because we want to project onto we want to project such that we sort of best as best as possible, preserve shapes and areas for California, since that's our area of interest. And so to project onto that projection that we identified, the EPSG 3310, we can use this ST transform function from the SF package, apply it to our shapefile, and then the second argument to this function should just be the CRS code that we identified. And so when we apply this function, it's going to, without us needing to do anything manually, it's going to change the projection of the shapefile to this projection that we want for our mapping. And then you look at the top of this file again after that projection, you can see here that in some of this information at the top, that's printed at the top, it tells us that we now have a projected coordinate reference system. And this is the one that we asked for. So now we can start thinking about making a map. So first, let's just use ggplot to simply map the county boundaries, not mapping anything fancy, just making a map of the California county boundaries first. So to do this, we can use ggplot basically as usual, where we feed in as our data set our shapefile for the California counties, properly projected. And then the only thing we need to do to tell it to plot the county boundaries is add this geom_sf function. And so when we run this, oops, did I not load in my packages? Okay. Okay, now I'm in the wrong spot. Okay, here we go. So when we run this, we see that we get this map that looks like California and has the county boundaries. So again, we get this just by running ggplot, feeding in our shapefile as our data set, and using this geom_sf command. And then, of course, what we actually want to do is to map this melanoma incidence data by county. And note that when we look at the county boundary file, it has this column called GeoID. And this is just what are called GeoIDs in this shapefile are the same thing as the county FIPS codes that we saw in our melanoma data file. So remember, in the melanoma data, we had these FIPS codes. They are equivalent to what this shapefile calls GeoID. So to merge our melanoma data into our shapefile, we can just merge based on matching these GeoIDs to the FIPS codes in the melanoma data. So run that here. So now we have this gives us a shapefile, again, where our melanoma column is added in. So you can see here that the melanoma rate variable has been added in to the shapefile. And so now if we want to map melanoma rates, we can use a similar ggplot command where we feed in this merged data set, that's still a shapefile as our data. And then within the geom_sf command, now we want to tell it that we want to fill the polygons, we want to fill the areas with a color based on their melanoma rate, where the colors range from white to red, going from high to low melanoma rates. And then these other parts are just kind of like standard ggplot aesthetic stuff that I think you should be familiar with if you've worked with ggplot before. So when we run this, now we see we get this nice map of the county melanoma rates for California. The gray ones are areas where there was, are counties where there was no data, missing data. And so we can see that tend to get very high melanoma rates in some of these counties along the coast, as well as sort of in here on in the eastern, some of parts of the eastern parts of California. So then once we make a ggplot map like this, we can save it as a PDF or an image file, kind of in the usual way, however you normally do that, either by point and click or by using the save commands. These ggplot maps are really great for reports and publications, but what if we want an interactive map that allows us to zoom or to have information pop up when we hover over certain things? The ggplot mapping functions, to my knowledge, can't yet handle interactive maps, but there is another mapping package called Leaflet that can help us create interactive maps. And so I don't want to spend a ton of time on Leaflet because there's a lot of good information online about it. And honestly, whenever I make a Leaflet map, I don't remember all of these commands. I have to either go back to the documentation or use ChatGPT to help me write the code for these Leaflet maps. But just to give you a sense of what Leaflet mapping can do, let's try first just using Leaflet to map county boundaries, just so you get a sense of the basics of what Leaflet maps tend to look like. Oh, and actually, when we plug in our county shapefile into Leaflet, it actually gives us a warning that the projection isn't what it wants. So Leaflet actually requires that input data simply give lat-long coordinates with no projection. There are ways that you can override that default, but it's quite involved and it's beyond the scope of what we're going to do here today. So let's just create another object where we convert the spatial information to lat-long rather than the projection that we've been working with for California. We can do that here just again by applying the st-transform function, and this CRS code tells it that we just want basic lat-long information. And so now when we try that code again, we see that what we get is this nice interactive map with the county boundaries plotted. It has this base map, which is the OpenStreetMap base map. You can change that, but we aren't going to be doing that here. So you can change and use different base maps, and you see that you can zoom in and out. You can see basic features of the on the base map through the along with the county boundaries. And so this is just a very basic Leaflet map. We of course would typically want to map our melanoma rates. And so again, I'm not going to go through every line of this code for the Leaflet mapping in detail, because a lot of it is very like in the weeds, sort of nuanced options for different things that are easy to kind of have ChatGPT or the Leaflet documentation help you with. I more just want to make you familiar with the types of maps Leaflet can make in case you're interested. So if we want to make a Leaflet map with our melanoma, mapping our melanoma rate data by county, we can do that by adding adding this information within the add polygons function. And what you can see is that now we have this interactive map with the melanoma rate information for each polygon layered over top, um, which can allow us to zoom and do various other things. I just want to quickly mention that Leaflet can also make really fancy interactive maps, like the one shown here. You can feel free to pick around in this code if you want, if this is the kind of map that you're interested in. But this map basically also allows for hovering to get information. So when you hover your mouse over a county, it will tell you the name. It can tell you the name of the county and the melanoma rate for the county. So again, not going to go through that code in detail because, again, whenever I make leaflet maps, I just always have the documentation or or ChatGPT help me to sort of do these kinds of bells and whistles on the map. But just want to make you aware of the types of functions and features that Leaflet can provide in these interactive mapping settings. So now let's think back to our other class of spatial data that we wanted to be able to work with, which is raster data. And how would we import, process, and map that in R? So remember, rasters are these data files that have a whole bunch of equally sized cells or grid cells or pixels. And rasters are actually just simply image files. So they're sort of regarded by your computer as something very similar to just a standard JPEG image. And so in the simplest case, a raster file might just store the value of a single variable measured at each grid cell. So maybe a single climate exposure variable measured at each grid cell. And in that case, we call the raster a quote unquote single band raster, meaning it only measures sort of one feature, one particular feature, in our case, usually a climate feature at each grid cell. You can also have what are called multi-band rasters, that store values of a whole bunch of different variables, or maybe the same variable measured at multiple time points for each grid cell. And you can sort of think about them as this stack of single band rasters where we're measuring, again, maybe different features in each one of these elements, or we're measuring the same feature over a bunch of different time points. And so raster data can come with a variety of different like file extensions. So it can sometimes actually be hard to identify what is and isn't a raster. I think the most common one is a TIFF or GeoTIFF file extension. And that's what we'll work with in our example here today. So in R, when we're working with raster data, the Terra package is kind of the gold standard these days. There are several other package options for raster data, but Terra is really nice because it's very computationally optimized, which is helpful because often these raster data sets are very large. So it'll help us read in and manipulate the data really quickly. Also, this package can actually handle a wide range of spatial data types beyond rasters. So it can also actually handle vector data as well. Although the SF package remains sort of far more popular in general for working with vector data, which is why that's what we introduced here for vector data. But the Terra package is quite flexible and can handle vector data as well. And like the SF package, it has really great demos and documentation associated with it. So you can also install this package on CRAN using the usual syntax. So you might go ahead and try installing that package if you haven't already. Oops, for some reason, this is moving backwards instead of forwards. So for our raster data interactive example, I went ahead and downloaded and lightly cleaned some data on UV index across California. So these data come on a raster to us from the NASA Earth Observations data set. And so these sort of lightly processed data that we're going to use in this example are provided in the Google Drive folder in this file uveindex.tiff. And so let's switch back to the R code to show how to import these raster data into R and make maps with them. We'll also show briefly how to link raster and aerial data, which is a common sort of preparatory step we want to do in climate epidemiology studies. We commonly want to sort of align rasterized climate exposure data with the aerial health outcome data, which usually means that we're just computing an average or a weighted average of the values of the climate variable across all the raster grid cells that intersect each polygon. So in our example, for instance, we might want to compute a weighted average UV index level across grid cells within each county. And then we could link the county level UV index data with the melanoma rate data and do more formal sort of statistical analyses. So let's see how we would actually implement that in the R script. I know we're running kind of short on time, so luckily the raster data are pretty straightforward to work with. So hopefully you can see my R script again here. So let's go ahead and read in that UV index data that is provided to us on a raster using the rast function from within the Terra package. So here, this rast function just reads in that UV index raster file and saves it in this UV object. So first, let's take a look at what happens when we just print out that UV object. We see that it's a spatial raster. We also can see here from this, this line here that this raster data set is already has the projection applied to it that we wanted to work with, the EPSG 3310 projection. So that means we don't have to mess with the projection of this raster data set, although if you did need to, you can just use this Terra project function, which does something very similar to the ST transform function from the SF package. You can apply it to your shapefile to project it onto whatever projection you need. Note that when you print this UV data object, you don't actually see any data. So to actually be able to see what the data values in the raster look like, I like to do this, just like apply this as data frame to the UV object. Just to see, this X and Y give us like the coordinate informations for each sort of raster grid cell point. And then we see the associated UV values. So it's common actually just, base R plots actually work quite well for rasters. So you can actually just apply the base R plot function to make a map of the raster data. So if we do that, here's what we see. So you can see that when we map this raster, remember this is just a bunch of pixels where each pixel represents a particular spatial location and has an associated UV index value, which range from about 5.5 to about 8.5. And so this is nice, but how can we see where these pixels lie in relation to California? This right now just looks like a pretty colorful map, but it's not clear how these relate to California. So to do that, let's just overlay the county boundaries onto this shapefile plot from our SF object, our county boundaries SF object. So we can do that by just saying that we want to add the geometry plot for the SF shapefile with the county boundaries. And so when we do that, we can see we can see the county boundaries, the California county boundaries overlaid on top of the raster. We can also see that we have a lot of information here in this raster that is not restricted to California, but also represents sort of a lot of other space outside of California. And so if you want to get rid of all of those pixels that are outside California in your map, you can use this mask function within the Terra package, where your first input should be the raster data file, and then your second argument should be your shape file. In this case, our county boundary shape file, for which that we want to use to sort of constrain the spatial domain of the raster. And we've applied this vect function to the county shape file because it sort of puts the SF shape file into a format that's more compatible with the Terra functions. So you can see that when we now plot this masked shape file, raster file, we see that it more closely conforms to the county boundaries. There we go. So here I've just showed using base R for mapping rasters. You can also use, I would say it's most common just to use base R to map rasters. It does it quite well. But if you do want to use ggplot or leaflet to map rasters, I've given you examples here in the code for how to do that. But for now, given time, I'm going to skip over those and jump straight to how we actually link our raster data with our health outcome data to do sort of further analyses. So remember that I said that the most common approach to try to link raster climate exposure data with our aerial health outcome data is just to take an average of the rasterized climate data across all the grid cells within each area boundary. So in this case, what we might want to do is average the UV across the grid cells whose centroids fall within each county's boundaries. And you can do that very easily using this extract function within the Terra package, where your first input should just be your raster file. Your second input should be your shape file, which again, we've applied this vect function to our county shape file because it puts the shape file into a format that works more nicely with Terra, the Terra package. And then you tell it what function you want to apply. So in this case, we want to take the average of the raster values of the raster pixel values within each of the polygons or areas given by this shape file. So we tell it that the function that we want to apply is the mean or the average. And so when we do this, we can see we save our data into this new object. We can see that now we have a county shape file that still has all of our relevant county information in it, but it now has this UV column added that tells us the average UV value across grid cells whose centroids fall within county 1, county 2, and so on. So there are a number of different ways that you could do this type of aggregation. Here we've just done sort of like the very simplest thing, which is just to simply average the UV across all grid cells whose centroids fall within a given county. But there are much more complicated ways that you could go about doing this sort of aggregation and linking of raster data with aerial data. We won't go into them here. So in the interest of making kind of a final side-by-side map of our health outcome data at the county level and now our UV index at the county level. Let's sort of first just make, let's make this object that was output by Terra, which is in one of the Terra shapefile formats. Let's convert it into an SF object just because I prefer to work with SF objects, which you can do using this st_as_ff command. So now we have this UV county object that is a standard SF object, and it has information in it both about the melanoma rate for each county and the average UV index for each county. So now let's say we want to sort of make side-by-side maps of the melanoma rate and the UV index for California counties. We can again do that just using the same type of ggplot SF map that we used earlier in the script, where we feed in our shapefile as the data object, apply geom_sf, first using melanoma rate as the variable that we're using to fill in the colors of the counties, and then making another map where we use UV as our variable that we're using to fill in the county colors, and saving both of those two maps to their own objects. And then if we want to plot them side by side, I think the easiest way to do that is just to use this plot grid command from the CalPlot package, which we can do and feed in both the map of the health outcome and the map of the exposure that we saved from our ggplot commands. What you can see here is that it gives you a side-by-side map, so you can sort of look at the melanoma rate and the average UV index for each county side by side. And also then you can take this data set that has both county level melanoma and county level UV index and use it to do, more extensive statistical analyses to look at associations between these variables. So I just want to wrap up. I know we're at time here. I just want to wrap up by saying, if you look at these slides, you can see that CAFE also has a lot more resources to assist with kind of more advanced spatial data processing of various types, and also several tutorials on how to actually do statistical analyses to look at associations between climate variables and health outcomes. And I've also linked to a bunch of other freely available spatial and GIS books for R that I highly recommend checking out. And want to remind you finally just to make sure you cite all software and packages appropriately when using R for spatial data in your publications and reports. So we are at time. I see that there's been a ton of Q&A going on in the chat. Thank you so much, Allison, for managing the Q&A. If folks I personally have time to stay on for another couple of minutes. If folks want to stay on, if there are any sort of big remaining questions that folks had about any of the stuff that I presented or anything more in detail, I'm happy to take any questions now. Thank you so much, Allison. I see that you are busy. I hope the issues with the packages didn't cause too many people to not be able to follow along interactively. Ty, hi. I think you're able to unmute and ask a question now.
Yeah. Can you hear me okay?
Yeah, I can.
Cool. Thank you so much. Yeah, this was a great webinar. I was just curious. I put this question in the chat, but I think there wasn't time. I was curious about, in the R script, in the raster analysis in lines, I think it was like 196 and 97. Yeah, where it was like using the Terra package to do a mask. It looks like, so 196 is like creating the mask, and then 197 is plotting the data within the California mask, and I'm curious about how in like 197 R knows to apply the version of like the masked version of the data. I guess like how R knows to link those two lines together, because I guess the mask isn't being saved as like its own object or something. And to me, it looks like in 190, I guess on yours is 196. I must have added a line in my mind somewhere, but in 196, it's like not referencing the mask directly, if that makes sense. So I was sort of curious, like how those two lines
Right.
cooperate.
Yeah. So here, this first line is just plotting the raster. And so this mask function is basically, you could actually take this mask function like out of the plot function and move it up into its own object. And so this is just like masking to cut out all of the UV raster that falls outside these county boundaries for California. And so this new object will just be that masked shape file, that masked raster file that sort of contains to just the pixels within California. And then this second line here is just overlaying. All it's doing is like taking that raster map and overlaying the county boundary map. So the county boundary map is, of course, already contained to just the county boundaries. And you're just adding it on top of the masked raster file.
Okay, thanks. That makes sense. Yeah, I guess like I see what you're saying. Like you could create an object, but you don't need to because the mask like permanently alters that other data set. And so then you can just layer on another thing on top of it. Okay, thank you. That makes sense.
Yeah, thanks for your question. Not sure if there was any other stuff that didn't get resolved that can get resolved. Oh, I see somebody's asking how often will you conduct webinars on this? We have, like I said, we have a few more advanced webinars that you can access through the links in the slides. But we plan to continue having webinars of various types, not just on spatial data processing, but we do have a regular webinar schedule coming up for the next few months, usually a webinar every week or two. And I believe, Elaine, they can find out information about that in the newsletter. Correct me if I'm wrong.
Yes, the newsletter that goes out always has information about the upcoming events, including webinars and workshops. And then you can also find that information on our LinkedIn or our website.
Thanks, everybody. Really appreciate all your engagement. Feel free to reach out to me with any additional questions. And thanks again to Elaine and Allison, who helped out with managing the chat during this. Appreciate it.